Sorry for joining late. I'll still take like 5 minutes for setting up and we can start from like 6:20 max. Okay. Okay, there we go. So this is like week 7 for us, and we still have like one more week to go, week 8, and that's probably next Tuesday. And after that, you're done. So your course will be done. If you have registered further for exams, then you'll have those. You'll be able to. So yeah, for that we'll have to solve the assignments and questions so that you can pass the exam with like flying colors there. Okay. So let's start with week 7. So this week is all about the Nernst equation that not Nernst, yeah, but we saw Einstein's equation in last week. And then later within that, we have an extra session. Uh, so till now, till sorry, not till now, but from last week, we have seen diffusion flows due to diffusion, flows due to forces, and an external active force if it's being applied. And then we tried comparing it. That's when we derived the formulation for what do you say that Einstein's equation. After Einstein's equation, we had a couple of questions about if it's directly proportional to the time and if it's not proportional, like if it's proportional to the square root of it. And there, like we also came up to an example where it was like example of 1D, 2D, and 3D. I suggest you to go through the derivation for it if at all you don't remember it at times. If not, the derivations are quite simple. Like those are based on polar coordinates. I've also posted the derivations in the week's content, so you can go there and have a look. Instead, the formulas are simple in case you can directly memorize them. So, okay, so this week is also all about the same thing, but instead it has two, three different like concepts. First being the Nernst equation, if you have went through the course slides, and then I wanted to introduce like we previously saw when like how to integrate when you have product of two terms, but that formula I thought is too strict and you don't know when to take which function first if it, like if you go through or if you see functions which are like one logarithmic function and one trigonometric or a trigonometric and an algebraic or one exponential function, or you have like a series of functions multiplied with each other, then which function to take first and next. Then we have Fourier series and Fourier transform, and with that Fourier transform will end up later, like probably next week the prof will be talking about more into statistics, simple statistical features like there are like mean, median, mode, and those things. Then there are also like spectral features, so you see the differences with respect to the curve's response, how the curve changes, if it's monotonically increasing, decreasing, if the trend is like decaying, those forms. So there are like how we studied when we were doing exponentials, but we are not talking about the same thing here. So he has just introduced some things into deterministic and stochastic nature of behavior of things for this week. Okay. So let's go through it. Yeah. So last time when we had that extra session, we looked into this, that this book reference was given and the book is also uploaded now. So if you directly go, you can get an PDF online copy of the book there on the session platform. Okay. So to begin with, I'm Jagriti. I'm a PhD scholar at IIT Gandhinagar, and I'm a PMRF TA for Professor Ranjit from IIT Bombay. Okay. So let's just first do the Nernst equation. So there was this example which was given in class that if you have a concentration of gradient of charges, so he was doing something with proteins and molecules, but let's just assume, okay, not assume, but yeah, here is what you have a channel. It's like hollow in here. So this is your channel. And this is where, let's say you have a higher number of concentration of some charges and here you have less number of them. Eventually what will happen, there would be diffusion due to the concentration gradient here. So there would be a diffusion flow due to diffusion in this direction, whereas there would be a flow, it lets it to achieve itself because these are now charges and charges eventually have some attraction against each other, right? That attraction in this case is like noted as electrostatic potential. Now, this potential occurs because if you might have like read something about anode and cathode, right? So if you have electrons coming from anode, they are like they get striked on this anode, like simple principle for X-ray. So like these are negatively charged and this is like positively charged. So they have a tendency to get towards it. So something similar phenomenon here also due to charge differences, what you can call it. So that's an electrostatic potential, sometimes also referred to. So the differences in between from one point to another point. Now this is a charge which is moving from one place to another. So it is being called as potential differences there. Okay. Now, due to this potential difference, we'll have a current flow. So this is a flow due to the charges flow, the charges which will be flowing due to the force which they are receiving. And that force is nothing but an external force which they are like experiencing on themselves due to the charge differences there. Okay. Now, simply to write this, you know how diffusion flow due to diffusion is, that's negative of this diffusion constant. And then you have this concentration gradient, right? When you have this one, and then you know for the second one, your this flow is given as concentration times your velocity vector. And we studied last time that your velocity vector can also be written as force divided by the 6 pi eta a, where this a is the radius of your sphere. Here you assume that the object that you're looking at is a sphere. Okay. After that, since this is the force in here, this is nothing but due to the electrostatic potential. So that through physics, it is nothing but it is defined as charge times the electric field that it is being experienced. Okay. Now, electric field is something a vector, which is nothing but has a magnitude and a direction it follows through. It's a field. So if you might have studied during your like class 11th, 10th, 11th, 12th, so something about the right hand thumb rule. We say that if potential is coming from one direction, current is flowing in another direction, the field, magnetic, electric field, there are like some laws for Lorentz law, nature's principle, those things, where you see that, okay, what's the direction of the field, in which direction is it going into? Like if it's perpendicular, parallel into the plane, outside of the plane, perpendicular, parallel to this axis. So these are things. So in this case, your charge times the electric field is how you define it. And this charge is nothing but from where is this charge coming? So this charge is coming because you had initially a concentration difference, right? Now, in this case, that concentration difference is nothing but given by this potential, right? And now from two different terminals, you have this potential difference. So how you write it as now, since again, it's also going from higher to lesser. So eventually you'll have a negative, lesser number of direction in the other side. So always you are comparing from inside to outside. You are never comparing from outside to inside. So hence you have a negative sign here, and then you take a difference, a gradient of that potential, and then x cap if you want there. Okay, just because we are representing it as a vector. Now, in this case, what you have, this is the electric field, the magnitude of the electric field that you're looking at. Okay. Now, if we just insert these things in here for the force, so this would be something as, now I'm just inserting as magnitude, so QC, and then you have force as d phi by dx, okay? Considering this is now 1 because it's unit, divided by 6 pi eta a, right? So you have these things. Now, the one due to diffusion and another one due to force will always, not always, but after a point until the system achieves equilibrium, these would be equal in magnitude, right? Both JD and JF would be equal in magnitude and opposite in direction. Now, when they are like that, equal in magnitude and opposite in direction, what you do is like you compare both of them, not compare, or you equate both of them, the magnitude of both the vectors, JD and JF. And if you have seen in the class slides how the integration is being done, it's like pretty simple. You take, let's say, let's just do it for now. So if you have this vector right here and you have QC d phi by dx, and then you have 6 pi eta a. Okay, let's just take C to this side back. So it will be 1 by C and then dC by dx, right? And this side, we have like this d6 pi eta a, and Q is right also constant here. So you have Q and then you have d phi by dx, right? You have all these terms here. Now, what do? You integrate all of them. And now, since we are considering from one location to another location, let's just add some position vector inputs to it. Let's say from x1 to x2 of dx and then x dx, and then from x1 to x2, right? Something like this. Now, here 1 by c dc. So this is nothing but x-axis cancelled. So 1 by c of dc is what? Will give you a logarithm, right? And this is from x1 to x2. Similarly, on the other side, you see that all other things are constant. You get this are cancelled. So only you are like, you end up with phi, right? So you have like phi with the thing that you need to substitute with. And these all constants would be outside. 6 pi eta a. So this is your phi, which will go from x1 to x2. Now, when you do that, you have the concentration to be evaluated with this position that is x2 and concentration with position x1. So let's just write it something as concentration of x2 minus concentration of x. And with property of log, you know that this can be written as cx2 minus cx1. So this is like if you have log a minus log b, you can write it as log a by b. On the other side, you have like phi of x2 and minus phi of this. So you write the same thing, d6 by eta a, and then this would be like phi x2, not phi x2, but like phi at x2 minus phi at x. Okay. So what that is, that's nothing but a difference, right? So you can write it as delta phi. So this is what your Nernst equation is all about. You see that when you have difference in potentials, difference in concentration at two different positions, that's how you can give quantify your answer. Now, if you want your entire equation in terms of phi, you can take all the constants to the other side. So if you do that, del phi will be this d6 by eta a by q times your concentration at x2 and concentration at x1, right? Till this point, is it clear? Yes, my speakers. I hope you don't have any doubts. Okay, so then from previously, we know that you can write this diffusion constant in terms of this Boltzmann constant temperature, and then you have the 6 by eta A. Now in here, the units are always like one is joules per Kelvin and another one is Kelvin. So Kelvin can be cancelled and this is joules. So in on total, this is energy. So this total also makes up to something as energy. So that's a ratio for it. Okay, so accordingly, you'll have not, this is not energy, of course, because now you'll have your diffusion units as meter square per time or seconds that you see. Okay, so this is how your diffusion constant is. Now, if you insert diffusion constant in here, you see that this is 6 BT and this is 6 pi eta a, and then you also have 6 pi eta a here by q, and then you have log of x2 by x1, right? Now these both are cancelled. So if you want to write this concentration or potential change or flux change from one position to another position, you can write both of them as this. I don't know if there is a particular example about it, but that's how you say that this is an equilibrium concentration at one position and equilibrium concentration at another position. That's how you just represent both of them. There were like no practical examples for these, so I don't know how it would be applicable. But this is something I do think so that the instructor wants us to know about. And I also saw in examples assignments, there were no questions next to it. But it's fine. It's good to know a relationship in between both of them, or either ways, you know, now the integral here are simple, and now you have solved like pretty big integrals till this stage. So you can solve this once, if at all, if it's being asked. But what you do need to know are like this, like this relations like this, which can be easily asked into some simple 1-2 marks numericals, or like simple direct numericals where you don't have any MCQs being given. Something as units for this term, units for another term. So everything that you see in here, you should know the units and dimensions for it. Either way, if you don't know, you see what physical quantity is being asked to you, and then try to relate it and try and derive it if you don't know at that particular moment. Okay, in here you might not know about this viscosity. So go read up about viscosity, see its units, how it is being expressed in terms of which terms it's being expressed. Similarly to diffusion also. If it's sometimes given in terms of, let's say, degree Celsius or Kelvin or Fahrenheit, then you might get confused at which unit to use. Or let's say for distance, you might use it as meter or or centimeter, then which one to use. So always fix to the SI units yourself and see that in which units is this final quantity being expressed as. If that's a different quantity, then you try and derive the, like if it's SI unit, so it would follow MKG metric. If it's another one, it will follow that CG and something as different, something different. So those things you need to know in this case. Okay. Then you have Fourier series. So what actually this Fourier series was like, so yeah, of course, this was one such person who came up with the series. So he wanted to say that that a function or a waveform, you can represent them as a combination of or a sum of all sines and cosines. Okay, so he just wanted to say that all functions we can make up using the combination of all this only two simple functions and we don't need many such different functions. But he gave a definition next to it that those functions should be periodic. If they are periodic, then only this series, this function, how you represent a function, you can define them using Fourier series. And Fourier series has its own formula. So how can you do so and when can you do so? So it's like at a particular point, if you want to evaluate a position of something, a direction, not a direction, but yeah, of course, position, a position vector, you can derive that position vector at a point, and the nature of the vector, you can derive it using Fourier series. Of course, you can look at the angle, like cos of some angle, sine of some angle. What that angle will reveal you is about the direction that you look at. But for direction, you need to do like tan inverse of the y by x component. So that's an additional step there. Okay. So that's how Fourier series you define it. So this is like a DC part, or how you call it as an average here. So this is when your all these constants are zero and you only have the energy of the function. So that's a naught by 2. And then if you, so you all know till this point that cos, these are like even functions, right? So f of x is equals to f of minus x in this case. So hence, this is the even part of the Fourier series, whereas this one is an odd part because for sine, you have f of x is equals to f minus of f of x, right? So both these functions are different. These are different coefficients that you look at here, an and then bn, and then this is as a naught. So given if you know the function yourself, then you can evaluate the other function. So a naught, bn. Now, how do you do so? You see the function, the waveform that we started off from right from the beginning. Like if you do see a square waveform, you should know that the square waveform is existing in between these points. Now, after that point, it's not existing. So that's zero. Now, you know something about the x-axis. So you identify or provided some limits. Now, you know what its height is. Let's say h here. So for it is h in between x1 to x2, it is 0 in between x2 to x3, later following the same thing. So it's a periodic function. You can apply a series to it. Now you know where it is h, where it is 0, where it is again h, where it is again 0. So in that case, you know the function. Now try and find the function, trying and find the coefficients from there. That is the point from where this limits will actually give you the true nature of the function that you're trying to represent it with. Of course, there would be some cases that since you are evaluating it within two strict limits, the function that you get, that function won't be the smooth as that you're looking at, but will have some ringing in it. Ringing as in some sense of noise probably there, which won't directly reflect the true function itself, won't be as smooth as the true function that you're looking at, but it will indeed tell you that what this function would be towards the end if you're looking at it. Okay. So you can also, so yeah, till now you know about dot products and something here that you should know. So let's say if I write a vector as a times I cap plus b times j cap, let's say c times k cap. So can like how can we evaluate b here? What would be my b? The coefficient b if I want to say, right? So what it would be? It's nothing but your vector times b, right? Sorry, what did I write? It would be as your vector times the j cap vector. Okay, you'll multiply the corresponding components with this ones, and so this is not multiplication, but essentially it's a dot product in between two terms. So you can either write this dot product as how I told you previously, combination of cos theta, or in case if you want to evaluate what that product will come into, you can integrate it. So you'll get the sum of the area, where like the area under the curve for that particular component that you're looking at there. Okay. So from there only, the definitions for this curves come from. So if you have, let's say, a naught here, a naught by 2, you can evaluate. So a naught is nothing but the average of the function that you're looking at. So this a naught, you can write it as directly integrate your function itself. So it won't have anything, but instead it does has a cost component in a naught, which is nothing but cos of 0x. So 0x is essentially 1, right? So this would be f of x. Now, since you're taking it an average and looking at in between certain limits, so let's say if I'm including from 1 to pi, so I can integrate it from negative pi to pi, and that's an average area for it. That's 1 by pi, what I've written there. You can also write this one as 1 by pi. You can write it as 0 to 2 pi, and you can add a 2 over here. Okay, so limits can be interchanged in those cases. So that's just from where and where you want to evaluate the function from. Okay, now given for an is something for the cost function, right? So how do you write an as? An would be something as f of x times this cos component, what I'm having. Let's say nx in here. The here it's written in with respect to time. Let's say a position vector, what we are trying to evaluate it from. Okay. So similarly, same limits if we want to see, it can be like this. Okay. Similarly for bn would be 1 by pi of negative pi to pi. It would be f of x and then your sine component of nx dx. Okay, understood. Now in these cases, you always will need to know that if you are multiplying these two terms. In here, so when I was studying, before doing this part, my instructors, like, they taught me integration in a way that you need to know which function is this. Okay. For that, I have a slide right here, but till now, I guess I'm not, that's why I added this one. Yeah. So you need to know which function you have there in there for the Fourier series to be evaluated against. And for the same instructor, Professor Ranjit, he gave some identities in class which were like this. So if you have, let's say, sine A plus B, it is like sine A and cos B. These are like some identities. How I used to remember them was like, if you have A plus B, and this is for sine, so you'll have sine A first, cos B plus cos A sine B. But do remember that all of these identities come from sine rule and cosine. Feel free to ponder upon them whenever you have time, if you at all are interested. So yeah, if you have like a triangle which has all directions and sides of A, B, C, you can write it as sine A by A. You can write it as sine B by B. You can write it as sine C by C. This is simple one for sine. There are also for cosine. There are also for tangents. So the tans ones, and from there people came upon from this. So these themselves also have a derivation. Okay, but no need to look at that again. For cos is like a even function. Okay, so what it will do is like it will take all cos components by itself and then it will add a 9. Now for cos, if you have a plus sign here, it would be inverse of it. If you have a minus sign, it would be inverse of it. Again for tan, you can directly take these terms and add it inside here. So you can have like sine A plus B by cos A plus B, and you can evaluate, like, do LCM differently, HCF differently. Then you can come upon these terms. I'm like pretty sure that you'll get these terms itself. But if you cannot remember them, there's also a trick. So if you have like tan A plus B, it is like tan A plus tan B by 1 minus this one and tan A minus B. So it's like that. Not giving you tricks here to remember them, but that's how I used to do when I was doing. Okay. Now there were like 2-3 definitions that Prof gave during the class. It was something as, if you have a sine, let's say mx, and then if you have sine nx, okay, dx. So he told that if you're trying to evaluate in between negative pi to pi, this would be equal to pi, and you have a delta mn term, right? Now this is only valid if you have m is equals to n, both are same. It will give you zero when, sorry, it will give you zero when this is both are not equal to each other. Essentially, delta, evaluating it at delta makes the function pi itself. Okay. Similarly, if you have something for cos mx and then cos nx dx, negative pi to pi, it also gives you the same thing, pi of delta mn, where m is equals to n, and it is 0 when both are not equal to each other. But there is a case where if you have both of them together, so an even function and odd function together will end up doing nothing. So they'll just destroy everything. So that's just 0. Okay, so that is for any values of n comma n, it is always 0. Okay, any value insert in there. So these are like some identities, and this is how you compute these terms. Prof has like during the class he gave that which one how do you do, and like if you have this term series, which particular coefficient would it be. So till now I do think so it is like pretty intuitive to you that how you should do it. Like it's if you look in here, it's simple. So if you have, let's say, just insert fx, then it would be cos 1x, then f of 2x, then cos of 2x, like that. So your coefficients go on. Similarly, if it's like this part of the component, it would be like n equals to 1 to n till the point that you're realizing it till. Okay. Okay. So after this point, yeah, one more thing. So for this trigonometric identities that you look in here, you also have always, you let's say if you, for one such case, if you are trying to do sine of a plus b plus, let's say I'm doing something as sine of a minus b. Okay, so in this case, what will you get? You'll get this. You're summing this two, right? So this gets cancelled out. So what you get is 2 of sine of a and cos of b. Okay, so identities like this are nothing but used in here to do this integrals, right? So if you are just memorizing at this stage that, okay, this is simple, and this identity is simple, it all comes from identities like this. So these are like some basic identities. I'll uh, tell you to see, look on them. If you don't want to look at its derivations, the identities are simple enough to just grasp it on. Look at its addition parts, try adding both of them. I'm only saying for the sine and cos ones, the first four, add them together. So yeah, just add sines together, subtract them, add cos together, subtract them, and see what it gives you. Now, these are the terms that will eventually be integrating with, okay? And now for integration, what you do is you integrate u, v, and then let's say both u and v are like a function of x, so you might integrate with dx. Now, initially we did something as product rule, integration of product rule, and we derived it, right? If you might have remembered. So there we did something as keep the first function constant, and then we had like, if we get the first function as u as, and then we had its own derivative, and from that derivative insert it back in. So that's something a lengthy process. The same formula we'll be looking at, but from some different perspective now. So the process when you have two terms together, okay? When you have, let's say here, if you have u of x and then you have, let's say, b of x, dx, okay? Similar as, let's say, if you have x times log of x dx. Now, how do you do? Which function do you integrate first? Of course, now since you know the formula, you can insert it into, but which order do you go with? Now, there's a order that you need to follow there. You cannot directly take, let's say, here, if the prof would have, now these are like both signs, so it's fine. But now here, one is sine and one is cos. So in between trigonometric series, them also you have an order to follow. Which function first you should go? Like here, let's say you are doing a, like evaluating a coefficient with a trigonometric function. So how do you go? Which one should you take first then? Okay. So this is something as islet that I have studied, and like mostly when I did study, they had this acronym. I don't know what they use now, but that's how integration by parts happen. So this is like a conventional or traditional way how they call it by, and that's how it is. So the first one, I, stands for inverse trigonometric functions. The next one, L, is for logarithms, A is for algebraic, T is for trigonometric, E is for exponential. Pretty simple. Like you now know this is inverse, this is log, this is algebraic, this is trigno, and this is exponential functions. Okay. Now, if you have functions like that, let's say this one, can you tell me which function would be first? Which one should I take as my u and v? So in this case, my u is first and v is second. So which one should be u and v? If I have x of ln of x dx.
I think land would be first and then X.
Yeah, yes. So the log would be first and then x. So I would do it like you write under it or beneath it that this is first. Now, why this is first? You have L first, then you have algebraic here. So how the order goes is you'll always look at it as 1, 2, 3, 4, and 5. This is like a order of priority for the functions that you're looking at. Okay. So here also, since you had x log of x, log comes first, so that's first, and this is second. Then you have your formula that. Now, if you want to integrate two functions together, you keep the first one as it is, integrate the v. Here also integrate the v. So first is you keep the first function constant, integrate the v, minus you differentiate the second function. Why differentiate the second function? That's because you perhaps find a tricky function inside there, or a function that might help the integration of this, the second one, to go easy on. So it will make its life easy there. Okay. So you differentiate the first one and integrate the second one. Overall, integrate both of them. So if we have to do for, let's say for this function, x of ln of x dx, How do we do? So this is our like first function and this is second function. First function will keep as it is. We won't differentiate it yet or integrate it yet. Nothing. Okay. Because we know the integral of, oh, sorry, we know the differentiation of it. We don't know the integral of it. What comes? No idea. We'll have to perhaps substitute it with something else. Okay. Then you integrate the first one. Sorry, the second function. So integrating the second function will give you something as x squared by 2, right? Then you have a minus sign. You differentiate your first function. So this is like 1 by x. You integrate the second function, x squared by 2, right? Dx. Minus, you have this as x by 2. 1 by 2 comes out. And you integrate your x. So that's like x squared by 2, right? Again, this is like indefinite integral. You'll definitely have a c there. This is like x squared ln of x by 2. So what it comes as x squared ln of x by 2 minus minus x squared by 4 plus c, right? So that's how, let's say, in class or lecture, we came on this. So prof showed us that if you want to evaluate for a series, let's say for this series, you had like multiplied this function um, with cos. So the function, so we took the function as x itself and we multiplied the function with cos and we multiplied the function with sine, right? In one case, it was easier to follow back. Other case, it wasn't because, yeah, the limits, how you look at the limits there, the limits from negative pi to pi, and for cos, it eventually went out to be 0. But if you now want to do it for sine, how do you integrate it? So he has only given the formula for it, but it didn't derive it. So I thought let's just do it. So we're like, let's say it is not let's say, but that's how your definition for Bn goes as. And then you have x of sine of nx dx. Now, which is your first function and which is your second function here?
This is first and sine is second.
Yeah, I guess. So x is first here, sine is second here. Okay. So how do you do this? You'll be 1 by pi, keep it as constant. You'll keep your first function as it is, right? You'll integrate your second function. So that gives you cos nx by n, right? And in that you want to evaluate it from negative pi to pi. That's it. Now your second one, minus, you differentiate the first function, right? Yeah. You differentiate the first function, so you get 1. And you integrate your second function, so you get cos of nx. So integrating sine is negative cos x, right? So you have a plus here by n. Right. Cos, I know. When do you get a negative? That's when you have a negative. Yeah, by n. And then you have dx here, right? Because you are evaluating it from negative pi to pi. So you have 1 by pi, you have x, you have negative cos of nx by n, negative pi to pi plus. Now here, what is sine? Cos is derivative, sorry, integrative, that is sine, right? So you have sine nx by one more n, right? So that's n square. Now you integrate it from negative pi to pi. So whole function, you can write it directly as evaluate the function from negative pi to pi. Okay, clear till this point? Now we have like x minus, so this is not minus, multiplied by negative cos of nx by n and then sin x by n square. Now let's just say for first limit, if you are looking at let's say function at x equals to pi, I'll only see the ones which are inside the bracket here. Okay, so only this term. So what it becomes? It becomes as pi negative of cos of, this would be n pi, right? And then this would be n plus, this is sine of n pi by n square, right? Uh, yes, by n square. Now, if you see for x is equals to minus pi, what you have there? So if you insert x as minus pi and you have a minus sign also inside, so that will become as positive, right? So this is positive pi And cos is an even function. So rather you insert a cos pi or cos of minus pi, it will eventually give you a positive sign there, right? So that is cos of n pi by n plus this would be, and what is sine? Sine is an odd function. So you have sine of negative pi as negative of sine pi, right? So this is like this by n square. Now you want to take a difference in between both of them. So let's just take difference. So if we subtract both of them, the first one minus the second term, what do you get there? So this would be minus the second term. So this would be negative 2 times pi of cos of n pi by n, right? And the second one, if you subtract that, the second sign, this will be positive, right? So this is 2 of sine n pi by, this is in bracket, by n square. Okay. Now, if you insert it again into the bracket here, if you take this term and you insert it right here, what you get is 1 by pi of, right? So you have negative 2 pi cos of n pi by n, and then you have plus 2 sine pi by n square. Sorry. You insert the terms inside, so that makes it as negative 2 cos n pi by n plus you have 2 pi n square of sine n pi. Okay, this is the one you have. But now you know that sine is 0 at all pi's, right? Sine is 0 at all pi's and cos is negative 1 at all pi's. So you know something as sine n pi would always 0. Cos n pi would be all negative 1. But now since this is n pi, it would be power n. Howsoever n it would be, because cos 2 pi is n. So that would be like plus 1. Okay. So now you insert both of them. So this is like this. And this all term is 0. Right. Now insert this negative sign itself here also. So this makes it as negative 1. And since you are adding that negative sign there, so it would always be an n plus 1 by n. So that's how your Bn is when you multiply a sign component to it. Okay. Now, again, these terms will also differ if you have an even function, if you have an odd function, if you take a subtraction of them, you add them, multiply them, those cases, in those scenarios, mostly for even and odd, they all do change and vary. Okay. So defining that, we saw island, and then there's Fourier transform. But I guess there next to Fourier series, there was also a part for Fourier series as in its Euler's form. Okay, so what was there in this Euler's formula was that, if you might have remembered, we learned something as this, right? Where we had of e raised to I theta can be written as cos theta plus I sine theta, right? So similarly, in this case also, they are writing as e raised to I nx. So that can be written as cos of nx plus I of nx, right? And for the same also, you can write its Fourier series as a form of a summation of, so the same series that we just wrote now, you can write it as infinity, negative infinity to positive infinity, have some constant in here, times e raised to I nx, right? This I nx is what? Now you know that. Now, one I is what? It is square root of minus 1. An imaginary number is written as that. Okay. Now, what is this Cn? This Cn is nothing but it is similar to that. 1 by 2 pi, negative pi to pi. It is evaluated as f of x, and then you take an inverse of this. So minus I nx, and then you dx, right? So these are like terms for it. If you study signal and systems or signal systems processing, you'll get to the derivations for them. If you are just looking at for maths, there is no need to go into its own derivations because it has different principles, causality, for linearity, and those things. So for you to derive this term. So nowadays people don't even derive, they just go with the definitions that you have. Okay. Now from this, how do you relate it with the an and bn that we had previously? Simple is your an is nothing but sum of both cn taking it positive and negative. So you can see the definition for this one. You expand this inx as this quantity that we have written, add both of them, substituting n as n and n as minus n, add both of them. You will see the same formula that we wrote. For bn, it is I times Cn minus negative n. Okay. And Cn, you can also write from both of them as we can write half of An minus I of Bn. How I represent it personally is as cos is always as positive, sine is always as negative. Even functions will always have a positive sign, odd functions will have a negative sign. Hence the case here, here, and here. Okay, if that makes your life easy. And then in terms of the average function that we had, so Cn can be written as half of A naught, all average functions. Now, these are the conditions where you have n as positive. This is a condition where n is equals to 0. And if you have something as negative numbers, so for those negative numbers, you can also write Cn as half of the combination of both An and Bn. Okay, of course, Bn would be with an I right there. Okay, so this is how different series are. So this is through Euler's formula, you can write the series. One thing that makes it compact is the exponential part that you have here. So you no longer need to evaluate the units again. Just evaluate Cn right here and you're done and dusted. Okay. So what does this Fourier series does was that we saw that it helps us to evaluate a function as a combination of both sine and cos, right? Then you have something as Fourier transform. Now, this Fourier transform, when it came into picture, it made life easy for everyone, especially for the one who are doing like processing on their own computers, big data processing and those things. What it does is it will convert your data from a time domain. It is like a domain conversion processing to frequency domain. Now, frequency you might have heard of is something like inverse of time, right? So in frequency, it appears that everything goes faster. You have all processing as very faster. Hardware complexity is very lesser in those cases. Hence, people go with Fourier transform. Oh, sorry, yeah, Fourier transform, but they go into frequency domain. Like there are different parts to it. You have like a discrete Fourier transform. You have like a fast Fourier transform. You have like a continuous Fourier transform. You have different ideas for it. You have something as short time Fourier transform. You have those cases. So you can evaluate the Fourier transform in different limits at different stages. The length of the function can be different. You have those cases in there. Okay. I guess my screen got stuck or what? Oh, okay. Back, it's back. Okay. So in Fourier transform, this is the conversion that you do. So you essentially know that you're converting some spatial domain matrix, let's say x, y, z, comma, t, all into the frequency domain spatial maps, or let's say temporal maps. So it can always be converted into frequency based domain or inverse of your spatial domains. Okay. So here meter is essentially, m is essentially meter. So inverse of your spatial domain that you're looking at that. Okay. So if we are evaluating a Fourier series for a periodic function, which is a repeating function, now you know, let's say in Euler's form, previously we saw that how do you represent it with respect to like e raised to inx, and then you have an cn term to it. This is how frequency transform will do. So what frequency Fourier transform will do is it will convert, let's say if you have a function as same terminology I'll use as prof, f of x. Now this f of x, you can convert it into g of k being the spatial frequency that you're knowing over there. Okay. So that's how the ideology he gave was this k would be always inversely proportional to length. It is inversely proportional to time, those metrics. So it's always inversely proportional to the ideal domain that we are working into. Now, if it's being concerned with frequency, if this is time, then the other one can either be frequency, but now since we are evaluating this function as f, so we cannot write it as frequency. So let's just use some omega. So omega is nothing but some your angular frequency. You can write it as, so omega is always 2 pi f, right? You can also write it as 2 pi by t. Okay. Or you can also write it as n pi by tau. So in some cases for a short duration time. So your definition for Fourier transform goes as this one, the second one. If you have a function time domain, you take a multiply it with an inverse exponential. So that's like e raised to minus I omega t dt. If you want to take into another side domain f of t, you validate. Now, why do we have this 1 by 2 pi? It's because of the frequency time domain conversion right here. Okay. Since we already saw this is like 2 pi by t. So now if you are evaluating it with respect to time, so this becomes as 2 pi by omega. So hence the differences that you see, it's inverse of it. So this domain will essentially have an inverse there. Okay, inverse of time domain. It's like omega by 2 pi right here. Okay, you can write them like that. Now that's why you have this one here. Uh, with that, yeah. So always this time domain and frequency domain conversions are convertible or reversible. Okay. You can always convert from one domain to another. The time domain you can take from frequency domain and frequency domain to time domain. So vice versa, this things goes. Okay. Now you can also write one function as a combination of, or let's say a summation of the series. So you can either write this Euler's as you know till now is like something as cos of, you can write it as cos of omega t minus, sorry, plus I sine of omega t, right? So if you do so, and if you write it as a combination of both sine and cosine, then what is this integral? Integral is essentially the sum of the area against with or within to any limits that you're looking at. So that essentially becomes a summation there, and that's how you can also write it as a series. So these are some things, and there are like also some rules and formulas associated with Fourier analysis. But it's fine. Like till this stage, you don't have any further applications or extended versions to it. So stopping here for Fourier transform makes sense. So if I just want to show you something, so if you take a cosine function, its Fourier transform makes it as a this single frequency, your delta function. So this is a delta function. What this function is, this is nothing but it represents a function at omega, let's say this, and the value is only 1 when omega is equals to 0. Okay, so delta, the characteristic for a delta function is that the value for it will always be, so it at delta of 0 only it is 1. Okay, so that's a delta function, an impulse function that you're looking at. So this impulse only exists at the time t equals to, let's say, t naught that you are defining it with. After that, it decays. It won't decay. So in real life, producing an exact delta or an impulse function is at all difficult, right? So what people do, they'll make a series of signals, let's say a combination of sine and cosine. They'll take its Fourier transform in frequency domain, and then the further analysis they'll do with the single frequency domain. Now, because here, if you take its time domain response or if you take its frequency domain response, it will remain essentially the same. The Fourier transform of this function is essentially one. It's unit. So it won't affect you anything. It won't make your hardware even complex. So that makes your life easy. If it's for a sinc function, something that you see a bands over here, you have a rectangle for it. If you have a Gaussian function, it also follows similar to delta. It is same as Gaussian. Double exponential and those things are fine. Those are like some advanced functions there. Okay. After that, we had something as statistics. So that was like a last part for it. And what statistics do mean is, now, like you might have done till this stage, something as, sorry, mean, median. These are like our basic parameters. Mode, standard deviation, variance, skewness, right? Then you also have something as kurtosis. You have something as bias. You have something as coefficient of, oh, sorry. You have something as this coefficient of variation. These are all some methods and not methods, all metrics which people have come up with, all statisticians have come up with so that you define the function itself. Okay, so these are like all different methods, not methods, yeah, metrics or parameters through which you can define your function as. Okay. So here what you're looking at are like two models, one being a stochastic, another being a deterministic. How their name sounds are like essentially the meaning behind it. The first one as deterministic one is nothing but you'll have no differentiation there. So you'll always get an exact quantity. So it is similar to how your Newton's law goes or your population growth or Ohm's law equals to IR. So you have exact value or answer for it is known to you, right? Now here you have no random inputs. You have a solution to a specific set of values. The results are always the same. Okay, you have no variations there. Whereas the second one, if you see for stochastic models, you have uncertainty there, you have randomness there. There are the variations, the input might also change. And what comes with randomness is your probability, right? So here you define everything with probability. Either it can be conditional, joint, different types of probabilities. So you always have an estimation of probability for the different outcomes that you are evaluating it against, and the difference will always be the same. Similarly, let's say if you're if you're tossing out a coin, if you're rolling a dice, then you have something as this Brownian motion that we studied when you were looking at diffusion, this zigzag motion of the particles, which is arising due to the stored potential and moving kinetic energy, later being converted into temperature in those. And let's say stock prices, which always goes up and down. So that's the stochasticity that we are looking there at. Okay. And in biology, if you want to look into randomness, this randomness in particles or the molecules that we are concerned with, those always come with this Brownian motion. So motion can be because of the inherent stored energy in between them. Motion can be due to the temperature differences in between both of them, in between the current differences of the particles, impedance differences of the particles, and hence things. Okay. So do you have any questions till now? Or else we can jump to the assignment questions then. Any questions? I hope it was clear.
I had one question.
Yeah, go ahead.
Uh, in the integration of the sine mx and sine nx, what
Mhm.
exactly is delta mn? Is it a constant?
Oh, that formula. This one.
This, yeah. Yeah.
Yeah, so this is essentially so what I just showed you. So this is, let's say, it's a function, this impulse. So this delta is nothing but an impulse at an axis where you have both mn and same to each other, then only this is one unit. That's it. Where both of them are
Okay.
not equal to each other, let's say sine of 3x and sine of 2x. So both functions will never, won't cross each other.
Okay.
So hence it would be zero. Similarly for cos.
Okay. Okay. Thank you.
Okay, then I guess we can jump to the assignment then. Assignment. Okay. So here, so now you know which of the following is an even function here. How do you evaluate an even function? If it's an even function, what do you have here? Do you have a positive sign or negative sign?
Positives.
Yeah, so that's positive. So which of the following is an even function?
T square.
T square is an even function. Next one. So here, just see how you write the Fourier series, right? Have something as this, then you have something as this, and then you have this. Of course, you have summations in between. Okay. So you have the Fourier series. If A3 is 5, B6 is 2, all other coefficients are 0, what is the function? So you have n's here, but the values for them are given, and all other are 0.
Will be the third option.
Yes, it's the third option. So since it's like A3, so the function associated with this would be 3, 1. So you have cos 3x, and this is like B6. So this would be 6, so it would be sine 6x, and this is 2 here, and this is 5 here, right? So this is 5 cos 3x plus 2 sine 6x. Next one. Imagine that you have a shape of bimolecule, which is like f of x is sine 2x. In the Fourier series analysis, which of this will represent the function? So when does your sine 2x come in the series? Again, like visualize the same series.
The first option.
First option. Why the first option? Because this is like B2 as 1, B2 as 2, B1 as 2, B2 as 2. Now here you only see sine of 2x. This is like sine nx. N is equals to 2. So essentially you have to look at B2 and B2 being 1 here. Okay, so that's the only option. If the protein can be represented like a linear function given by f of x as x, on this, what is the Fourier series for this function? So here, think, I'll like give you a hint, think smartly. Like don't just directly start writing. But if a simple function is given to you like that, look if the function is even or odd first. Now we know in this case, f of x is x, x is an odd function, right? Now for odd, if you have a Fourier series, the even part would be 0, right? So what you end up is only the bn and sine part. Now you do that.
So it will be the first option because there's
Exactly.
only sign.
The first. Yeah. Yes. Here. Assume that the concentration of a protein varies like a periodic function, then which of the following are correct? So if you have a periodic function, what are its properties? That the function will repeat itself after a time t, right? It did not be a even function or an odd function. Either ways, it's vice versa. You cannot say that a periodic function is always either a even or an odd function. So when it, yes,
It will be the second option.
it's the second option. Because periodic functions like repeat themselves after time t. So this is the period of the function that we're looking here at. Okay, so that's a property for it. Then this one, what is n? Sorry, what is the value for this when n is 52?
Two.
Sorry,
Two.
yeah, this is even. So that what makes it like 1 and 1 plus 1?
Ma'am, can you please explain the fifth question?
Fifth question, this one.
Hmm. Hmm.
Yeah. So for a periodic function, so let's just look at sine function, okay? So we have this again, after a point, it's going like this, okay? So this function, like this is 0, pi by 2, pi, 3 pi by 2, 2 pi, and then it will repeat, right? So one whole cycle is 2 pi, again 0 to 2 pi, okay? So this is the period of the function, t. So this is the period against which this function is repeating itself. So it's only asking us that if it's a periodic function, what is the property for it? So this can be a case if it is asking us for this function itself, direct function if the graph for the function is given to you. But if it's not the case, this cannot be the case either because periodic functions can either be even or odd. Why? Because this was an odd function, right? Still it is repeating after time t. If you look at cos, okay, now it has started from here, it will end here, right? Again, start from here, it will end here. So this is also periodic. It also has a time t. After every t time, the function is repeating itself. So that's a period here. Okay. That clear?
Yes, ma'am.
Okay, next question. So what's the value of 1 plus cos pi n when n is equals to 1? So we essentially have 1 plus cos of pi. What is cos pi?
-1.
So this is 1 minus 1. Okay. This one. So you need to find the value for this one if you have both sine and cos together. What will be the answer here? Do you need to integrate it? Okay. Here's this question. So we just studied about delta, right? The properties of delta function. That delta at that x value where it is standing at x is equals to, let's say, x of a or x not something. Only at that particular value it is 1. After that it's all 0. Nowhere nothing. So here you look, what's the value for delta, this integral x square and delta of x minus 2.
Will it be
So if
0?
sorry, what?
Will it be 0? Since
So if you see delta function, this delta function is 1 at x equals to 2, right? If you do as x minus 2 is equals to 0, you have x equals to 2. So at x equals to 2 only, this is 1. So in between negative infinity to infinity, this is only giving you a definite value at x equals to 2, that's 1. So you'll evaluate this at x equals to 2 itself. So this gives you, that's it. After that, this is the last one that we also saw. What's the Fourier transform for delta of x? So for delta of x, if it's always your Fourier transform gives you a unit. It won't ever be a function because it's only valid at x equals to at that point where you're looking at, but the amplitude for the function can be ever growing. It's like infinitely growing function, but in real life we evaluate it as one. So that's unity. Okay. Simple functions that you need to remember can be something as delta. This is something as direct delta, how they officially call it, or they also represent it as impulse. Okay. If you give a function or system a input of delta or an impulse, okay, this output that you get is a response of it. And this response is what your Fourier transform is. Okay. In this case, when you gave a delta t, this t is only valid at, let's say, t equals to 0 here or t equals to t naught here. So whatever that value at the function at that time t is, that's your output. That's your Fourier transform. In this case, it's unit. Other function similar to it is Gaussian, which will also give you Gaussian. Now, why this function are directly evaluating themselves? So there's like a simple logic here. The function that you're looking here, delta, it's like it has sum of like all million forms of frequencies that you can look into. It is encompassing all of them, all sums of sines and cosines that you cannot even see it here because it's just unit. Similar to as how white light has all spectra of different lights. And if you shine light on it, you spin a color or disk, you'll see all different lights being reflected. Similarly, you have Gaussian. Gaussians can also be represented as like combination of all other functions or series all together. So Gaussian essentially remains a Gaussian there. Okay, these are like simple functions, only two functions there itself. Other functions do have their own different complex Fourier transforms, but at this stage that's fine, and you only need to know Fourier series more properly for this scope of for this particular course. Okay, any doubts? Questions?
No, no doubts.
Okay. Thank you. Thanks for joining then. We'll continue. Last week, we'll have one next Tuesday. And if you have any further questions till then, you can accumulate all them together and can let me know that at that time. Okay. Thank you.
Thank you.
Ananya, do you have anything? Okay, it's not then. Okay, then. Let's close this session. If you have any further questions, you can let me know on the second class, the last class, Tuesday, next Tuesday. Okay. Thanks for joining. Bye bye.